Okay, so the purpose of this video is to provide some illustrations of how you can carry out multi-level modeling using the STATA program. We're going to focus on carrying out a two-level multi-level model using data that was downloaded from this website right here. They're the data sets, and the example is coming from this book. Basically, just downloaded the SPSS data file and converted it to STATA for the purposes of the illustration. The data is school level data, or actually student data with students nested within schools. So the variables that are associated with the data file are over here. You'll have school code, ID, gender, SES, and so forth. If we open up the data file and take a look at the data, you'll see that in this file right here we have a variable for school code. There are about 419 schools. We have students nested within those schools. These are the student identifiers in the data set. These are the identifiers for students within schools. So these first 12 students that we see right here are associated with school 1. The next 13 are associated with school 2, and so forth. We have our primary outcome variable at level 1 is math achievement. So we're using this variable right here as our level 1 outcome, and we're going to use SES, student level SES, as a predictor of math achievement. In the data file, we also have, there's gender coded 0 and 1 for male and female respectively. So that's another level 1 variable, but we're not going to focus on that in this particular illustration. We also have SES mean, and basically these are the average SES levels for the students within each school. So you can see right here, these values are all exactly the same, and it's reflecting the average of these students' SES levels. So this is basically going to be treated as a contextual predictor at level 2. So we have level 1 student SES and level 2 school level composite SES as predictors of math achievement. So we're going to start off our analysis with a random intercept model, and basically the random intercept model is utilized in order to help to make a determination as to whether or not HLM is an appropriate strategy, and whether might we also consider something like least squares regression. And so the basic idea is that if you're drawing random samples out of a population and there's no clustering kind of effects, no dependent observations within clusters, then OLS regression makes more sense. But given that students are nested within schools, those students within the individual schools are probably going to be more similar to each other than they are between schools, and so that clustering effect produces a lack of independence in terms of the observations on our dependent variable, and so so it makes sense to consider multi-level modeling with this particular data. And as a first step, we typically start with a baseline model, which is a random intercept model. And what that means is that there's no predictors that are incorporated in the model. We're only studying variation in the intercepts across the level 2 units. And what that translates into in this kind of model is that the intercepts are basically the school means on the dependent variable. When we start incorporating predictors into the model, the intercepts are still means, but they're adjusted for the presence of the predictors that you include in the model. So we're still fundamentally looking at variation in means, but we talk about it in terms of varying intercepts. So we can run our random intercept model in a couple of ways through STATA. We can use drop-down menu, or we can use syntax. So this is the syntax that we're going to use for our analysis, but I thought I would illustrate both just to give you an idea about some of the menus as well. So to run our analysis, we'll go to statistics, we'll go down to multi-level mixed effects models to linear regression. Here you'll see that we have 2 estimation methods that are available to us: maximum likelihood and restricted maximum likelihood. The example in the text from this example right here in chapter 3 uses restricted maximum likelihood, but we're going to stick with maximum likelihood in this demonstration. Okay, so in terms of the where it says fixed effects model, what we're going to do is we are going to highlight our dependent variable, which is math for math achievement, and we're not going to include any independent variables in the model. So because we don't have any fixed effects at that level that we are interested in studying. But we do want to model the random variation and intercepts across the schools. So I'm going to click on Create, Level Variable for Equation. I'm going to select School Code right here, and then leave everything else as it was. So now this set of specifications will model the random variation across schools. So I'm going to click on OK. And so now you'll see our output. And so here, in terms of the output, the coefficient that you see right here, this is basically the grand mean across the schools. And this is basically a gamma. I'm not very good at drawing these things, but gamma. And this is the grand mean or for the intercept. And what that translates into is that we can say, well, across the schools, the average math achievement was 57.674. We have a significance test right here, which is really not terribly useful under many circumstances because we're really just testing whether this coefficient is significantly different from 0, and so it's not terribly useful under many circumstances. Down here we have the variance components. We have the residuals at level 1 and the variation and intercepts at level 2. So these right here are essentially variance components. So you can think about it this way. At level 1 we have prediction errors for each observation, reflecting the deviation between a given observation and the mean for the given school. So that's just the difference between each student's score on math achievement and the school mean. And what we want to do is to model or study the variation in those school means, or in the residuals at level 1. So that's level 1. And then at level 2, we have the variation in intercepts. And so each intercept is denoted as reflecting mu 0j, and we want to study the variation of those intercepts. Okay, or this is actually kind of reflecting the deviation between a given school mean and the grand mean. So we're essentially studying the variation in those school effects, if you will. So down here we have the variance estimate for the residuals and the variance estimate for the intercepts. And what we want to do is to test these to see if they are statistically significantly different from 0. And so you obviously we have our standard errors right here. And interestingly, we have no printout of any kind of z-test or anything of that nature. And so it's a little bit confusing when it comes to trying to make a judgment using the confidence intervals. So I kind of created a little calculator to run a test of these effects to see if they are significantly different from 0. So this is it right here, and basically all we do is just put the variance estimate here, standard error here, and we can generate a p-value for essentially a one-tailed z-test. So basically what I'll do is I'll just kind of highlight the variance of the residuals and put it here where it says level 1 residuals, and then the standard error for the residuals. I'll move it over as well. And then we have the variance of the intercepts and the variance and the standard error associated with that variance estimate. Okay, and so then we have an observed z value, and we have essentially for the variance components test, we have it's a one-tailed z-test. Just kind of for comparative purposes, I want to just show you what's going on in SPSS and show you how this was derived. So I'm going to run an intercept-only model in SPSS, and I've already specified the random effect and everything, and asked for all the statistics that I'm asking for through STATA. And so here you can see down below, there's our grand mean across the schools, and these are the variance components. So these are the estimates, and you'll notice that those estimates are exactly the same as what we see in SPSS. The standard errors are the same, and then we have the walled z. So the z value for the residuals is 56.802, which is kind of going back to our calculator. You have the 56.802, and for the intercepts, the variance of the intercepts, it was 10.348, and you can see there's the 10.348. So that's how it was derived. So basically just taking a ratio of the estimate to the standard error, it gets us a z value. And we basically are going to use a one-tailed test. So the interesting thing in SPSS is that the p-value is actually printed out for a two-tailed test, but it really should be a one-tailed because you can't have a negative variance. So we're only testing in the upper tail of the z distribution. And so that's why this particular value right here is kind of noted that we're using a one-tailed test. If we wanted to model the covariance between the intercepts and slopes later on, then we would use a two-tailed test, and so there's an adjustment for that for this particular test. So at any rate, that is the random intercept model. If I want to use syntax, I will just go down to the command line. I'll type in mixed, so that's the command to run the multi-level model. I'll type in math, which is the name of the dependent variable, 2 vertical bars, and then type in the name of the level 2 predictor, which is school code, and then a colon. Just make sure that the variables in terms of the caps, whether the upper and lower case, match what's the variable names in your data set. So when I run the analysis, this is it right here, and it's the same information as what we had before. Oftentimes you want to follow up the multi-level model by generating the intra-class correlation coefficient or various fit indices. So we're going to use the estat command here. You can use it through the drop-down menus, through the post-estimation drop-down menus in STATA, but it's just a little quicker if you can just do it this way. So we're going to type in estat ICC, and what the ICC is, the intra-class correlation coefficient, is giving us an index of the proportion of variation in the level 1 outcome that is occurring between the level 2 units, in this case between schools. So we can interpret this to mean that about 13.7% of the variation in math achievement is occurring between schools. And that's really a non-trivial amount. So it actually suggests then that multi-level modeling is really probably the best way to go. I can also type in estat IC and get information criteria such as the AIC, Akaiki's information criteria, and Bayesian information criteria. And this can be useful for making model comparisons. You only want to utilize these kinds of criteria though if you're using maximum likelihood estimation. Now let's try another model where we incorporate a fixed level 1 predictor with randomly varying intercepts. So in this case, I'm going to add in socioeconomic status as a level 1 predictor. And the basic idea is that if I'm laying out this predictor with socioeconomic status, I'm essentially saying that I'm modeling to allow the slopes, or basically fixing the slopes to be the same across the school context, but I'm still allowing the intercepts to randomly vary. Later on, we might wish to allow the slopes to randomly vary as well as the intercepts. But in this case, if I am generating this kind of model, I'm fixing the slope to be equal across groups, but then allowing the intercepts to randomly vary. So let's do this through our two routes. So if I go to statistics, multi-level mixed effects models, linear regression, in this case, I'm going to click on this button, go down to SES, and leave everything else exactly the same. So now when I click on OK, we have our output. You'll notice that in this case, SES, this is our regression coefficient for SES, and it is positive, and I would interpret this to mean for every 1 unit increase on SES, there's a predicted increase of roughly 3.88 units on math achievement. So there's a positive predictive relationship. We have a z-test here, and the p-value that's printed out is for a two-tailed test. So if I wanted to carry out a one-tailed test, testing a directional hypothesis, I could certainly do that by just splitting the p-value in half. But it looks like SES is a significant positive predictor of math achievement, meaning that students who tended to have higher levels of SES also tended to demonstrate greater levels of math achievement. The intercept now is math achievement adjusted for the presence of SES. So in other words, this is the grand mean on math achievement adjusted for the level 1 predictor in the model. Now we have the variance components still at level 1 and level 2. So we're essentially want to test whether the residuals at level 1 are they statistically significantly different from 0, and also are the intercepts at level 2, is that variance significantly different from 0. So I can, again, I can just use my little handy dandy calculator, and I will just put in the level 1 residual variance estimate here and the standard error. And we'll do the same for the intercepts. Okay, there you go. And so we can see we have significant variation in the residuals at level 1 and significant variation in the intercepts. Again, just by way of comparison, I'll run the same model through SPSS with SES incorporated as a fixed predictor. And you will see then that in this case, the Wald Z values 56.642, 56.642, and 6.422 and 6.422. So exactly the same. So that, so that's indicating then that we have significant variation at level 1 and level 2 that may be accounted for by adding in additional predictors. If I want to follow up with the interclass correlation coefficient, I'll just type ESTAT ICC, and you can see now the ICC is at 0.052. So in other words, after controlling for socioeconomic status, our clustering effect actually is decreasing. So basically, 5.2% of the variation in math achievement is occurring between schools after we control for the socioeconomic status variable. So, and then, again, if I want to model or use syntax, let me go back here, then essentially this is what I would do. So you can see it says mixed math is the dependent variable, and now I'm adding in the name of the predictor variable, the fixed predictor variable at level 1, which is SES. And then we have the school code as our level 2 identifier. So rather than just typing it in, I'm just going to go ahead and copy and paste it in. And so there you go. There's our same information as what we had before. Now, let's say we want to model, incorporate a level 2 predictor, which is take the school mean for those students and as a predictor of variation at level 2. So in this case, when we add in that the school mean on SES, we're essentially modeling variation in the intercepts across schools. We're modeling variation in the intercepts, which are, again, adjusted means on math achievement, and we're modeling that variation. So we're indirectly then modeling variation in individual level math achievement through the study of variation in the intercepts. So to do this, in this case, we're just going to do it through both routes again, just for illustration purposes. And so now where it says independent variables, I'm going to click on SES mean, and there you go. And so now when I click on OK, I get the coefficients, and you can see right here we've got SES mean. So that's a level 2 predictor, and SES is our level 1 predictor. So you can see that both coefficients are positive and both of them are statistically significant in the model. So the level 1 predictor, SES, we basically infer that student level SES is a significant positive predictor of math achievement, and then school level SES is a positive predictor of math achievement as well, through the as it's positively related to the variation in the intercepts. Okay, so in terms of looking at level 1 and level 2 variances again, we can again test whether these are statistically significantly different from 0, and so we'll just plug this information into our little calculator. So there's the level 1 variance, standard error, level 2 variance estimate, and the standard error. And so now you can see that both are still statistically significant. So there's still variation to be explained at both levels. I'll compute the ICC, and you can see now it's actually drops to 0.038. So basically, there's still clustering effects that are unaccounted for by adding in the level 1, level 2 predictors. So at any rate, there you go. Now let's try another example where we have a fixed level 2 predictor or rather fixed level 1 and fixed level 2 predictors with randomly varying intercepts and slopes. So we're basically building on this model by allowing the slopes for SES at level 1 to randomly vary. So in this case, using our menu option, find it again, there it is. In this case, what we're going to do is we're going to maintain these independent variables as they were, but now, this equation right here, this is allowing random variation in the intercepts. If I want to add randomly varying slopes, then I have to create the opportunity to do that. So I'm going to click on create. Go back, put school code in right here, and then the independent variables in the equation, I'm going to highlight SES, because I'm going to allow the slopes for SES to vary across the groups. Notice that we have a couple of options. In this particular case, if I stick with independent, what that translates into is that we have the variance in the intercepts. If you can kind of imagine a variance covariance matrix where we have the variance in the intercepts, and then we have the variance in the slopes, and I'm going to denote varying slopes as mu, I should say 1j right there. So we have the variance in the intercepts, variance in the slopes. If we leave it as independent, then the covariance between those two coefficients is 0. If I specify it as unstructured, then what that translates into is that we have the variance for the intercepts, variance for the slopes, and then we have the covariance between those two, which is the mu oj, mu 1j right here. And then it's repeated up there in our covariance matrix. So at any rate, things can get a little bit more complicated if we start allowing random variation in the slopes, because then we have to make a decision as to whether we just focus on the variation in the intercepts and the variation in the slope, or do we also build in the covariation between them. So if we leave it as independent, what's going to happen is that when we run the model, you'll still see that we have down here, we've still got the variance in SES and the slope for SES. We have the variance in the intercepts, and then we also have the variance at level 1. So again, this is the variance in the epsilon ij's. Then we have the variance in the mu oj's. Oops. And then we have the variance in the mu 1j's, which is for the slopes. So we have then a variance estimate for the slopes, intercepts, and again the level 1 residuals. So here we can test this out again, same way by using our little calculator. So at level 1, and then the intercepts, variation in the intercepts. So I'm just going to put it in here. And then now we have the slope. So now I can put in the variance estimate for the slope. And there you go. So you can see then that the slopes appear to be exhibiting significant variation across school contexts. So what that, what that suggests then is that not only do the intercepts vary, but now, we have different slopes. So in other words, just kind of to give you a little bit of a visual of what I'm talking about, if you imagine that, each of these lines has a slope associated with them, and then they also have their variances. So we're talking about the variation in both. And so if there's significant variation in the slopes, then the next question is why? What is it about those school contexts that might be producing variation? And so then we might add in level 2 predictors of that variation. And that's where you move into modeling cross-level interactions. So you'll notice that in this particular case, again, this is essentially, by the way, this is the syntax for running this particular analysis. So again, if I just kind of plug this in down here, you'll notice that that there's no specification concerning the covariance matrix for the coefficients. The default is essentially a variance components analysis or approach, which, if I was in SPSS, what that would translate into is that I would have, there again, there's the mean here. I would have my effects, my fixed effects there, and then the random effects would include SES, and then the covariance type is variance components. So, if I run that analysis, these are essentially the same values that what we had when we generated our results using STATA. So that is essentially using variance components. I might also choose an unstructured covariance matrix, which would allow the estimation of the covariance between the slopes and the intercepts. So if I'm doing this through the menu option in STATA, essentially I would go to equation 2 down here and where it says, and click on edit, and I would move down and click on unstructured. So then when I click on OK and then on OK here, then you can see that now what is estimated, I have the variance for SES. So that's the variance estimate for the variation in slopes and the standard error, variation in the intercepts, so right here, and then we have the covariation between the slopes and the intercepts. And so you can see it's negative. And what that basically means then is that in those situations where basically there's a negative relationship between the slopes for SES and their intercepts. So without going into too much detail, I will just illustrate this again using my little calculator. And we can test whether or not that covariance is statistically significant. So I'm just going to incorporate each of this information here. There's the variance of the intercepts, variance for the slopes, and then, variance of the intercepts and standard errors for the intercepts. And then we got the slopes right here. And standard error. And then we have the covariance. And so what I was saying earlier was that this test is actually going to be a two-tailed test because we're unlikely to really have an a priori hypothesis about the covariance between the slopes and the intercepts. So basically, what the negative coefficient would just mean that in schools where that have a higher mean, the slopes are more negative. Um, so that's basically what it means. So, again, by way of comparison with SPSS, if I wanted to do this through SPSS using the unstructured option, this is it right here. And so you can see you've got the variance for the intercepts. That's the first coefficient. So then you've got the variance for the slope, the second coefficient, and then you've got the covariance between the two. And so these are all the test values. So once that's basically done, once we've kind of identified what type, whether or not if the slopes are varying across the school context, then we might want to build in predictors of that variation. And so that's where we can model cross-level interactions. So in other words, the idea is that, if it's the case that, our slopes and, are varying across school contexts, we want to know why. What is it about the relationship between our school context that alters the relationship between SES and math achievement? And so then we can build in cross-level interactions using the STATA program. So just kind of, I've already actually run this through STATA, and what I thought I would do is I'm just going to take this syntax right here and plug it in to this box, the command box down here. And so, and what I've done also, I actually ran it using the unstructured matrix, and we end up with problems with model convergence. So allowing the covariation between the slopes and intercepts produced basically an inadmissible solution. So in this case, what I used was a covariance type independent, which is just essentially the variance components. And so at any rate, that's just kind of an illustration. There were some problems with collinearity and so forth, but that was just kind of to highlight the basic idea. And so, what we were basically testing is if there was a cross-level interaction, then that would signal that there are some certain contextual factors that may be producing variation in the slopes between SES and math achievement. So that's just a really quick follow-up. I didn't really intend to go too far into that, but that's just to highlight a typical follow-up to the question of, if the slopes are randomly varying, then why, and what is it about those school contexts? And so if we model cross-level interaction, then we're looking at how contextual factors are altering the relationships observed at level 1. So that concludes this illustration, and hopefully you find it useful.